Here we're going to look at question 13 from section 2 of the ENGAA 2018 paper. In this question we're told we have a stick which dips into water, creating a circular wave which moves at a constant speed. In this first part of the diagram we have a wavefront labelled Q, and then a time 1 second later we have the wavefront Q as well, and then a new wavefront which is created in that time period. We're told that the stick dips and creates a wave every 0.8 seconds. And then the question asks us to find the wavelength of our waves. If you would like to have a go at doing this question yourself, please pause the video now, otherwise let's have a go at doing it. Now, the first thing we can recognise from the information we're given is that if a wave is created every 0.8 seconds, and that means that the period of our wave is 0.8 seconds. So while this might not initially be useful, it's probably quite useful to recognise this time as being the period of our wave now, since we're almost certainly going to have to use this information at another point later on in the question. But after that, how about we have a bit of a think about which equations we could use to help us solve this question? Now, while we've got quite complicated diagrams with things going on, let's just think about basic wave equations, and the most basic of which is probably this, that the speed of a wave is equal to its frequency multiplied by its wavelength. Now this would seem initially quite useful because it's got a wavelength in it. Also, we know that the frequency of a wave is just equal to 1 over its time period. So we can rearrange this, or change this equation, so that the speed of our wave is just equal to our wavelength divided by the time period. So this would seem very useful because we want to find the wavelength. We have a time period, which is 0.8 seconds, but we don't have a speed, which suggests that actually, if we find the speed of our wave, then we can get our answer. So we've got to think about if there are any ways in which we can find the speed of our wave. Then just multiplying that by our time period will give us our answer. But since there doesn't seem to be any immediately obvious information in the question about the speed, let's have a look at our diagrams a bit more closely. So we know that in 1 second our wavefront Q moves out to this different distance, but we haven't got a distance on here at all. So how about we label one and call it D? So the distance from X to our wavefront Q at the time t plus 1, let's just call D. Then the next thing I've done is I've actually labelled our wavefront at time t on our diagram at t plus 1, just to make it a bit clearer what we're going to do next. So we know that in 1 second our wave Q has moved from this green position here straight out to this outer line, and since it was initially 2 centimetres away from the centre of our circle, from our position X, then we know that this distance is going to be D minus 2. So it's going to be the total distance minus this 2 centimetres. But why is this useful? Well, we know the time it's taken for our wave to travel this distance. And since we know the time it's taken for the wave to travel this distance, we can find its speed. So this distance, D minus 2, is going to be equal to the speed of our wave, C, multiplied by the time it's taken, which is 1 second. Now, this doesn't explicitly give us the speed, since we still have this unknown D. But it is slightly more useful because now we just have a nice equation with our speed in it, and we can see if we can try and eliminate D. So to do that, we need to try and find some other equation with D in it. Well, how about we consider another point on our diagram? What about if we were to consider the distance between our second wavefront and our first wavefront Q? Now this distance is going to be equal to the total distance from our wavefront Q to the centre. Take away the distance that our second wavefront has moved, 3.5 centimetres. Now this is going to be useful because we know that the period of the wave is every 0.8 seconds. So the time between wavefront Q and the second wavefront being produced is 0.8 seconds. So again, we know that for this distance, D minus 3.5, the wave has moved across a period of 8 seconds. 0.8 seconds, sorry. And therefore, just as we did with our green distance, D minus 2, we can say that this distance, D minus 3.5, is just equal to the speed multiplied by our 0.8 seconds. And now this is really useful because we have two different equations which have our speed c in it and our distance d. So with two equations and two unknowns, we can find out what both of them are. So there are multiple ways of solving these equations, but what I'm going to do is I'm just going to take one away from the other. And doing this, we get that 1.5 is just equal to 0.2c. So dividing by 0.2, we get that c is equal to 7.5 centimetres per second. Then, with this speed, we can substitute this back into our original equation for the wavelength, and by multiplying this speed, 7.5 centimetres per second, we find, with 0.8 seconds, then we find that our wavelength is just going to be 6 centimetres, and this answer is going to correspond with answer F given in the question.